Yes. 5 methods for actually solving them. Anybody remember what substitution, why we call it substitution? Yeah. You solve for one variable and then substitute it in the other equation. Remember why elimination is called elimination? Yeah. You want your x's, as JC just said, a 3x on the first equation, a negative 3x on the second equation, so they add up to 0. You make one of the variables eliminate. It's gone. Okay. Kramer's rule is going to involve something called a determinant, which is sort of like a matrix but easier. And then, of course, number 5 actually solves them with matrices. So that one will be a couple days down the road. There's your 5 methods. So substitution. Anybody have any memory of which ones you liked or didn't like? Anybody? Well, that's good. If you have no preconceived, oh no, it's bad or good, which method's which? Because let's put it this way. I have a preconceived notion of I know which ones cause most trouble. And well, let's do one first. Then we'll talk about why do we need 5 methods to solve the same kind of problem. Some are easier than others. Substitution and elimination are easiest if you have nice answers because they're quick. The algebra is faster. Kramer's rule and matrix equations are better if you have nasty fractions or decimals. They're going to be easier to work, and they're also very easy to program a computer to do. I didn't start out teaching Kramer's rule and matrix equations when I first started teaching, but computer technology has pushed a lot of topics down to the high school. Matrices I didn't learn until college, but because it's a major part of computer programming, we teach it now. So they all have their uses at various times, we'll put it that way. I'm actually going to do the same exact problem here by multiple methods so that you realize that, hey, dude, if I use any method, I still get the same answer. Big tip on these. Take the extra 10 seconds after you copy it down and double check that you copied it down right, because there is nothing more painful than doing one of these, all the work, and discovering you copied the problem wrong. That's ugly. You don't want to do that. So I am double checking that, yes, I copied the problem right. Okay. So substitution. You have to solve for one variable and then substitute it in the other equation. How do you decide what variable to solve for? Should I solve for the x and the 2x? Or the x and the 3x? The y's? Which variable should I solve for?
The x and the 2x.
And why'd you pick that one? Yeah. You can solve for any of them. It'll work with any of them. You can do substitution and solve for any variable. It doesn't matter. But when you solve for these variables, you're going to end up dividing that number over, so you're going to get fractions. So would you rather work with halves, fifths, thirds, or fourths? Halves. Halves are easier. So I always solve for whichever variable has the smallest coefficient on it. So that's always the first step. Hint, that was also on the journal. Okay, so if I need to solve for this x and the 2x, what am I moving? I'm adding the 5y, so I'll have 5y minus 22, and then what? Divide by 2. Which would simplify down to be 5 halves y minus 11. We usually do that step really, really, really good. It's right here, next step, where we make the mistake. After I've solved for that x, what do I do with it? Yeah. Since you solved for x, you can replace an x up here with that 5 halves y minus 11. The question is, which equation should you fill it into? The opposite one. You just solved the top equation. Why would you put it back in itself? So you're going to take this entire expression, this 5 halves 11 minus y, and you're going to go put it up here. Oops, wrong place. You're going to put it in for x in the other equation. Always do the opposite equation. So you're going to literally have 3 times, and in place of that x, we're putting 5 halves y minus 11. Is that it? Yeah. Finish the equation. Plus 4y equals 13. The idea is you now have an equation that's all y. So now, since the whole equation is in y, we can solve for y. So once you have it, that equation, first equation solved for, you're going to sub it in for the variable in the opposite equation. That's key. Right, so, okay dudes, algebra now. How do I solve it? Yeah, distribute 3, which is going to give me what? 15 halves minus 33 plus 4y equals 13. Okay. And here you kind of got a choice. Do you want to combine 33 and 13? You want to get rid of the fractions? You want to keep the fractions and just do common denominators? What's our preference? JC's voting for add 33. The rest of you aren't commenting. You're staring at me. Okay, since in this case, since they're all whole numbers, that's okay. A lot of times you will have multiple fractions at this stage. If you have several fractions in there, get rid of your fractions right away. In this case, 33 and 13 are easy to combine, but if those were numbers with fractions, you would want to get rid of all your fractions right away. But we can in this case. So that's going to leave me 15 halves y plus 4y equals 46. Okay. And I'm still going to encourage you, get your fractions. How? Yep. We're going to times that by 2. Just the first fraction? That'd be 15y plus 8y equals 92. Which is going to give me then how many y's? That's 23y equals 92. And what's going to happen? Anybody panicked? Will 92 or will 23 go into 92? No. Well, 23 is, but 23 times 4 is 92. So, we got an answer of 4. Are you done? We're finding where 2 lines intersect. So what's our answer have to be? It's a coordinate. We're looking for a coordinate where they cross each other. Do we have a coordinate? Yeah. We have a y equals 4. I need x. Okay. You can put it in lots of places to go find x. It's kind of your choice. We know y is 4. You can put it back in either of the original equations. Or, on substitution, you've got this equation here I've circled in green. X equals 5 halves y minus 11. That's x equals. So it's already solved for x, so it would be really simple to just go, oh, okay, let's do 5 halves times 4, and then subtract 11. What is 5 halves times 4? 10. And 10 minus 11 is really -1. So, as an answer, I want a coordinate because you're finding where the lines intersect. So how would you write this as a coordinate? Yeah, this would be -1, 4. And there's a solution. Woo! Y'all are supposed to look excited. The other class is not good. They need to know that you're excited. You're supposed to cheer. Yeah. Your enthusiasm is overwhelming. Okay. So that's substitution. Anybody remember liking that one? Not liking that one?
I think it's not too bad.
Not too bad?
It takes a lot of work.
It is the one I see the most mistakes in. There's a lot of room for algebra errors in substitution. So it's not my personal choice. If I'm going to solve a system and I get to choose whatever method I'm going to do, it's not going to be this one if I'm doing equations of lines where everything has a first power on it. Now, in December, we're going to come back and solve systems of equations, but our variables will have squares on them. Or some variables will have squares and some won't have squares. In some of those problems, the only way to solve it is by substitution. Other methods will not work. So that's why, if I have you do substitution now, then when you have no choice in December, you'll know how to do substitution already. Something to look forward to. All right, the better choice, my favorite, personal favorite. I'm an elimination fan. And I think this will be the one you guys remember the best because you probably have done it the most. So I'm doing the same exact problem, but I want to do it by elimination. Okay, well, first of all, I have a question. Does it matter whether we try to eliminate the x's or the y's? Can you do either one? Yeah, you can do either one. It makes absolutely no difference. We just need to decide. You guys want to ditch the x's or the y's? X's? Okay. So what's a number in common to 2 and 3? 6. Okay, but we want one of them to become a positive 6 and one of them to become a negative 6 so that they add up to 0. Okay. So I'm here and take the top one times a positive 3 and the bottom one times a negative 2. So that way the x's will add up to 6x and negative 6x.
Yeah.
What was it?
We should do negative 3, positive 6. So that way you're negative.
Oh, you're wanting to switch. Okay. They're wanting to switch because then you'll get rid of the negatives in the top part of the equation.
Yeah.
Okay, I can buy that. That works. So if I distribute negative 3, I will have negative 6x, but that'll make a positive 15, and a positive 66. Don't forget to multiply on this side. Always, people sometimes forget to do the other side of the equal sign. Okay, what's the second line going to be?
9.
6x.
I still have my 3 down there.
Okay, 6x plus 8y equals 26. Then what do you do with it? You've got the x's now have a negative 6x and a positive 6x. What's the, yeah, you literally draw a line and you add the two together. Just add down so that the x's will cancel. They're gone. And the y's will add up to 23y equals 92. Didn't we see that somewhere before? 23y equals 92. I believe that was the same thing you got when you solved substitution here. Down at the bottom, 23y equals 92. Imagine that.
So we should skip the one step right there.
So, yes, we can divide by 23 and we still get 4. Now on this one, where do you go get x? Yeah. You've got to go back to the one of the starting equations. It doesn't matter which one, whichever you think looks easier. You're going to solve for x. So what do y'all pick?
The bottom one.
The bottom one? Okay, she picked the bottom one. So I'm going 3x plus, and in place of y, I'm putting 4, which will equal, supposed to equal 13. That would give me 3x plus 16. And is it looking good? Are we going to get a nice answer? If I subtract 16, that'll be negative 3. And when I divide by 3, I will get negative 1. And once again, how do you write your answer? Negative 1, 4 is a coordinate. By the way, it is not a coordinate if there are not parentheses on it. Every year I have 2 or 3 people who, on test, will write me negative 1, 4, and we'll put parentheses on it. And I take a half point off every time. It's not a coordinate without the parentheses. And it's like, seriously, how hard is it to draw a parentheses? Ooh, zing, zing, that's really tough. I don't get it. Why is that so hard? So put parentheses on it. It's a big deal, to me at least. It's not an ordered pair without it. So, okay, elimination. We saw that a lot. Probably saw it maybe a little bit in geometry. Yeah, we should have. That comes back in a couple places in geometry. Okay, so last method of the day. We're going to learn Kramer's rule, but actually before we learn Kramer's rule, I have to teach you a new concept. You have to learn what a determinant is. Okay. I'm going to write you the definition, and I want you to tell me if you think you've heard this somewhere before. It's a square array of numbers enclosed between vertical lines. Does that ring a bell or sound like something you've heard before? An array of numbers. What's an array of numbers? Yeah. Rows and columns of numbers. Have we seen rows and columns of numbers somewhere before? In what? Matrices. But there's 2 things that make this not a matrix. 2 key words. It's enclosed in vertical lines. Matrices are in brackets. And the other key word is, what's it mean, square?
Oh, like there's 3 and 3 and not 3 or 4.
It's a 2 by 2 or a 3 by 3 or a 4 by 4. It's got to be the same number of rows and columns. It has to be square to be a determinant. We are today only learning how to do 2 by 2s. Next class is all about 3 by 3s. We're going to learn how to do elimination with X, Y, and Z. And Kramer's rule with X, Y, and Z, where you can solve for multiple variables. It'll be great. Trust me on this. It'll be great. But so today we have to learn how do you do a basic determinant. I don't want to. So literally, a determinant looks something like this. It's square, it's a 2 by 2, and it's between vertical lines. Now, last block they were trying to call those absolute values. It's not an absolute value. It's just vertical lines are the symbol we use to indicate it's a determinant. Okay, the big difference is a determinant works out to a number. You simplify that and it becomes a single number. So determinants represent a single number. We're going to work that baby down into something. And it's actually really easy to do. I'm going to write you the formula first and then we'll work it. If you have a determinant with A, B, C, D in it, all it takes to work a determinant, you have to start in the top left corner. And you multiply diagonal. So you're going to take A times D, and then the biggie, you have to subtract, and you multiply the other diagonal. So you'll multiply B and C together. So you multiply one corner, subtract to the other corner. I cannot say subtract enough because that's the mistake I see on these. So take this one with the numbers in it that I gave you here. If I start in the top left corner with the 2, I'm going to multiply and get what? 2 times 7 is 14. I'm then going to subtract, and then, yes, I'm going to get a negative 12, so yeah, I'm really going to add that. And I have a value of 26. So that determinant has a value of 26. It works out to a number. Is that incredibly difficult? Okay.
You want to practice drawing the lines in between?
Okay, I'm not following you.
Like connecting into what times?
Oh, you don't have to draw the arrows in there. No, I won't draw them anymore probably. Okay, so, is anybody going, what on earth can this have to do with solving a system of equations?
Yeah.
It's these random numbers, and we cross-multiplied them, and we got this answer. What's it do for me? Well, if you take the numbers out of your system equations and you put them in the determinant in the proper location, it's going to solve our system of equations, and you don't have to ever work with variables. You only work with numbers when you do this method. It's pretty amazing. You don't have to do variables. And so the method itself is called Kramer's rule. Kramer was a not particularly famous mathematician. In fact, this is probably one of the few things he's known for. And I want to say this was at least, I think he was in the early 1800s, so this is a couple hundred years back when he figured this method out. But guess what? We're going to do the same problem again. 2x minus 5y equals negative 22, and 3x plus 4y equals 13. Oh, shoot, y'all should have stopped me, guys.